Good morning. Can you hear me? Yes. So it is my pleasure today to welcome Pasquale Blasi, who is a professor at GSSI, the Gran Sasso Science Institute. He just moved there from the Observatory of Arcetri in Florence, where he spent many years. And so you're starting a new group, and you're also a director of the astroparticle division in GSSI. So Pasquale specializes in the transport and acceleration of cosmic rays. He works on emissions from a variety of objects, such as pulsar wind nebulae, supernova remnants. And so he's going to talk today about the broad topic of his expertise. And thank you.
Bye. So thank you for the kind invitation. It's always a pleasure to come to IAP. Maybe it's better to move it here. Is it a problem for the recording if I move the computer down here? Okay, so the broad topic of this talk is acceleration and transport of cosmic rays, but I think what I want to do is to try at least to give a different twist to this problem. The origin of cosmic rays is always summarized in terms of what they are and what we see and how do we match what we see with what we think they are, and mainly in terms of acceleration and transport. I want to at least try to add to this point of view another twist. So I think we are at a situation in the study of cosmic rays that is pretty similar to what David Schramm in cosmology introduced as a inner space, outer space paradigm. In study of cosmology, what we do is to use the laws of particle physics to understand cosmology, which at first seems a little bit of a counterintuitive, right? Because you're studying the very large by using the laws of the very small. But that's something that we have understood through the years, that in order to understand what happens on large scales, you really need to understand the microphysics of things. Now, in cosmic ray physics, I think it is a very similar situation, because it is the laws of plasma physics and particle physics that shape what cosmic rays do on very large scales. And it is also similar to the cosmology paradigm, because in the end, in both cases, what we measure is just a bunch of very large-scale objects. Like in cosmology, you measure the curvature of the universe, you measure omega baryon, you measure, well, you don't measure omega baryon, you measure the CMB fluctuations, anisotropies, the strength of it, the fluctuations on top of the spectrum, and you say, okay, this is consistent with having a universe which is made of baryons, dark matter, dark universe, dark energy. But all of these things, you don't know what they are, right? I mean, we don't know what dark matter is, we don't know what dark energy is, and yet we talk about precision cosmology. Now, in cosmic ray physics, you do pretty much the same things. You observe things on very large scales, and when I say things are spectrum, mass composition, and anisotropy. These are the very three observables that you have in our field, and you try to deduce or to model this thing using a bunch of microphysical objects. You say that there is diffusion, for instance, which, as we will see, manifests itself in terms of interaction of a particle with a plasma or with a turbulence in a plasma. So the idea is that, yes, we do observe things on large scales in both cases, but we can infer some sort of microphysics from there. Now, this is a short summary of how things look like at the present time. This is a spectrum of cosmic rays, which extends, as we usually say, over many orders of magnitude in both flux and in energy. On the x-axis, I also showed the typical center of mass energy of several accelerators, just to point out that the energies that you observe in cosmic ray physics are quite a bit larger, at least at this, in this energy range. They're pretty much larger than the ones that are accessible to us in accelerator. But more or less we see power laws all the way through, which are kind of non-interesting from the point of view of physical content. We know that a power law does not have any scale in it, right? So it is when you see breaks on top of a power law that you start to see a hint that some physical phenomenon is happening. That's why people spend so much time on the knee of the spectrum and probably here on the ankle and the GZK. The interesting thing is that in recent times we have actually started measuring things which have a flux which is orders of magnitude below the main contribution. So not only we have been able to measure spectra of individual components like protons, helium, carbon, oxygen, so on and so forth, but also of electrons, positrons, and antiprotons. And they are tremendously important for understanding what is going on in cosmic rays. Now, I was told to summarize also things that are well known, but I think it is useful for everybody to hear all the stories again, just to understand what they really mean. One thing that in our field holds a particularly important stand is the so-called cosmic clocks. This is the very reason why we know that cosmic rays in our galaxy are diffusing instead of manifesting a ballistic motion. In a ballistic way, cosmic rays would escape our galaxy in a time scale of the order of 10,000 years or so, which is wildly insufficient to produce any kind of secondary products, both the electrons or antiprotons or boron or lithium and so on and so forth. The fact that we observe secondary products, and by secondary here I mean especially boron, lithium, and beryllium, is the proof that cosmic rays are spending in our galaxy a time which is in excess of the ballistic one by at least 2 or 3 orders of magnitude. Okay, so cosmic rays are not escaping ballistically from our galaxy. How do we know that? Well, because we know the abundances of elements in the solar system and in the galactic cosmic rays. The galactic cosmic rays are black here, and especially I think it's important this dip here, which corresponds to boron, beryllium, and lithium, which, as you know, are not produced in any appreciable amount in the Big Bang nucleosynthesis because the universe expands too quickly at that time. But at the same time, in cosmic rays, they are basically as abundant as carbon and oxygen within a factor of 3 or 4. Okay? Now, that is the proof that cosmic rays are spending in the galaxy a time which is of the same order of magnitude of the so-called spallation time of a nucleus of a carbon, for instance, in the galaxy. And this corresponds typically to a time scale of tens of millions of years rather than a few thousand years, which is the ballistic time scale. The second indication comes from unstable isotopes. So beryllium, for instance, comes in 3 isotopes, 7, 9, and 10. 10 is unstable with a lifetime of 1.5 million years. If you do this an experiment of producing these 3 isotopes in a fixed target, you see these 3 peaks roughly at the same height, but when you do this in astrophysics, you see that the 3rd peak of beryllium is almost absent, which means that it has decayed. So again, you can infer from how much beryllium-10 you see, you can infer how long the cosmic rays spend in a galaxy, and again, you get order of magnitude, the same time scale as above, so several tens of millions of years. So these 2 indicators are the main reason why we think that cosmic rays are diffusing in our galaxy rather than just going straight. When I say straight, I don't mean really straight because there are magnetic fields, but at least following a helix. So what we know is that they're not even following a helicoidal trajectory in the galaxy because they must be going back and forth several times through their trajectory. So how do we try to envision this? Well, people have done this a long time ago, and I'll just sketch what we think we understand. And this is, of course, a toy model, but it's interesting. So assume that you have magnetic field B0 that we will call an ordered component of the magnetic field of our galaxy. And then let me assume that on top of this field, I just have a small perturbation. Small meaning that the amplitude of the perturbation, this small b, is very small compared with B0 in strength, and also that it's perpendicular to the ordered field. And now you can just write the equation of motion for a particle in that field, and that looks like that. But this is interesting because this first term here, as you well know from elementary physics, only changes the component x and y of the trajectory. That's a helicoidal motion. But the second term does not affect the first, but it changes the pitch angle of the particle. So the cosine of the angle of motion of the particle with respect to B0. So now you can transform this, because the modulus of B is left the same. You can write this P, this momentum, as the total momentum times the cosine of the angle, so d mu in dt, and you can rewrite this in a simple way like that. And now you tell me, well, this is useless, because if I take d mu in dt and average a cosine over a long time, I get 0. And that's, of course, true. But it is also true that if you have a drop of ink in the water, the stain around the place where the drop fell is symmetric all over the place, so the average position is 0. That doesn't mean that the stain doesn't get bigger, right? So in fact, what you want to do is to calculate the square of this angle, and what you get is a couple of interesting things. The first interesting thing, it scales like time and not like square of time, and that's the symptom of a diffusive process, when a square of a quantity depends linearly on time. But the second interesting thing is that a resonance is developed when the Larmor radius of the particle, when the wave number of the perturbation is the same as 1 over the Larmor radius of the particle. So basically, if you have a fluctuation which is very small wavelength compared with the Larmor radius of the particle, the two ignore each other. If the perturbation is very long, well, the particle just surfs on it, but nothing happens. But when they are of the same order of magnitude, a resonance occurs and the angle of the particle changes discontinuously. And that is the process of diffusion that we talk about. So when you average over many wavelengths and you introduce a power spectrum of these perturbations, there you go, that you can calculate quantities that are interesting, like the time that it takes for the particle to reverse direction by 90 degrees, which is the time that it takes to go back to the place where it was. And that scales like inversely proportional to the power spectrum. So the more power you have in these perturbations, the faster the particle goes back and starts diffusing. And you can introduce a diffusion coefficient in space, which is basically the Larmor radius, this quantity here, times the velocity divided by the power spectrum. Now, this is the quantity that we tried, that establishes a connection between the microphysics and what we observe on Earth. Take into account that the Larmor radius of a GeV particle is only a fraction of the size of the solar system, so it's very small scales in a sense. But then what we see is on cosmic rays is affected by physics on scales of 10 kiloparsec. So the huge difference in scales between the two is one of the reasons why it's difficult to connect the microphysics with the macrophysics. Now, this is not the end of the story, because what I describe is what people call the parallel diffusion, but at the same time particles also try to diffuse perpendicular to the magnetic field lines. That's a process which is much harder to treat in a simple way, because it depends on so-called perpendicular complexity and other things like that. I will not enter into that detail, but it is definitely something that is being investigated a lot. Now we come to the other side of the story. One of the leitmotifs of this colloquia that I would like to give to this colloquium is to pass the information that cosmic rays are not only passive spectators of whatever happens in the galaxy, but they are actually modifying the environment in which they propagate. So I told you that particles diffuse, right? But imagine now a toy experiment in which I have a gun that is shooting cosmic rays towards you, and the gun is actually shooting cosmic rays just in the same direction. And then after a time, tau 90, that I called before, of course the cosmic rays are starting to diffuse and moving backward, right? Well, but that means that they are losing momentum in the initial direction. Where does this momentum go? Now, there are different ways of doing this kind of exercise, but one thing that one can do is to speculate that it does go. You can actually show that it goes, but it goes into perturbations of the medium. And so you can say that the momentum that the particles are losing in a time tau 90 is actually going into the growth of waves whose amplitude, whose energy density is b squared over 8 pi. They move with a velocity v wave, and they grow with some factor here that I have parameterized. And then by requiring that these two are the same, so you reach some sort of equilibrium, you get a growth rate of perturbations, which within a factor of 2 is the same that you get from very complex nonlinear calculations. But what this is telling you is that particles are diffusing automatically implies that they are actually producing additional perturbations in the medium. And also, these perturbations have exactly the same wavelength as their Larmor radius. So they are suitable for their own diffusion. So you understand that the implication of this is that cosmic rays actually scatter on waves which have their own Larmor radius, I mean the wavelength equal to their own Larmor radius, which means that they are able to actually provide by themselves the agents through which they scatter. This idea is at the very basis of the concept of nonlinear diffusion, that is having a huge spread. And this, one of the most impressive applications of it is cosmic ray acceleration. The idea about acceleration of particles in the universe dates back to Enrico Fermi, 1949, although what we call today Fermi acceleration has nothing to do with Fermi. Fermi was long dead when the idea was put forward. But the idea Fermi had is to have a lot of these perturbations going around in the universe, moving at random. And you remember before I told you that the average value of mu is equal to 0, which is equivalent to say that the average energy of the particle doesn't change, but the square of the energy does change. And the idea is very simple, because a wave with a magnetic field that moves has an electric field, which is v vector b, right? Therefore, the interaction of the particle with the electric field of the wave will change the energy of the particle. We just neglect this effect because the electric field is of the order of the alpha n speed over c multiplied by the b field, and the fraction is typically 10 to minus 5, so who cares? And that's the reason exactly why the idea of Fermi was brilliant but useless, because E squared is different from 0, but every time that the particle momentum changes, only changes by VA over C, and VA over C is typically 10 to minus 5. Which is equivalent to say that the time scale that it takes for particles to change their momentum by p, so to double its momentum, is about 10 to the 5 to the square, so 10 to 10 times longer than the time needed for deflection by 90 degrees. So usually you neglect this process, okay? And this process is, because of this 2 here, known as second order Fermi acceleration. In 1978, so 20 years, more than 20 years after Fermi passed away, people thought about an alternative idea, which is shock waves, which are ubiquitous in astrophysics. You can think of a supernova explosion, for instance, in which the energy that you inject is of the order of 10 to 51 ergs, and the mass of the ejecta is of order a few solar masses. You can calculate the speed with which the ejecta moves, and that's about 10,000 kilometers per second. The sound speed in the interstellar medium is of the order of 10 kilometers per second, so the object is moving with a Mach number of order 1,000 or so, and that implies the formation of a shock front. A quite peculiar shock wave, however, because it's collisionless. In other words, if you calculate the time scale for two particle collisions in a system like this, is more or less a distance between here and Andromeda, which means obviously these shock waves are not mediated by two particle collisions, but they are mediated by collective effects like instabilities, in other words. But we see these shock waves. These are 3 images of Casei, Tycho, and supernova 1006, and these bluish rims all around are the shock wave as seen in X-rays as produced by synchrotron emission of high-energy electrons. And I'll come back to those rims because they hold a special importance. This is an actual picture in Balmer lines of the shock wave of supernova 1006. So the idea is always that the plasma from the interstellar medium enters the shock wave with a high speed and slows down so that the gas behind the shock wave is a little bit hotter than it was in front of it. And the particle that crosses the shock multiple times sees this jump in velocity, u1 minus u2, and every time that it crosses gains an energy which is proportional to this change in velocity. Here, this is u over c in units of the speed of light. The beautiful idea, the beautiful implication of this idea is that for a strong shock, namely when the Mach number of the shock is much larger than unity, the spectrum is universal. It's typically e to minus 2, independent of microphysics. So all the stuff that I told you before about diffusion and so on does not enter at all in the definition of this spectrum. So the result is very solid, and people are happy about that. Unfortunately, however, it comes in through the window because the maximum energy that you can get to this accelerator does depend on the microphysics. Moreover, in order to explain what we see at the Earth, about 10 to 20% of the energy of the system must be transformed into accelerated particles. Okay? So this is the old idea, 1978. Nothing has changed for many years, except that there are a bunch of problems with this, right? So the first problem is that there is no chalk. Therefore, I cannot write. But anyway, oh, maybe there. So the first problem is that if you accelerate a spectrum e to minus 2, the integral of e to minus 2 times the energy between some injection energy and, say, E max scales logarithmically with the ratio. And that means that you can, if the system becomes particularly effective, this object can exceed the amount of energy that is in the system, rho u squared. So you know already that the system at some point must become nonlinear because it must forbid the system to inject in the accelerator more than the energy that it has. Okay? The second reason why you need more than just what I told you before is that if you calculate the maximum energy for a shock wave, even with extreme parameters that at the shock of a supernova, the typical numbers that you come out with are of the order of 1 GeV, which of course are wildly insufficient for cosmic ray physics, where the energies we observe are at least 6 or 7 orders of magnitude larger. So that means that either the cosmic rays themselves change dramatically the system around the shock, or the shock does not act as a good accelerator. So these are the hints that we need more than the simple theory we had before. So let's start from the first issue, so the issue of the energy. What happens if I put in this information? Well, what happens is that the standard shock wave that people are used to, namely that discontinuity is formed, so the velocity does something like this, right? So this is the shock front, okay? Something like this does not exist in nature, because what happens is that particles with low energy spend most of their time very close to the shock front, so close to what 1 is. High energy particles spend time here. Therefore, the pressure exercised on the plasma here is less than the pressure exerted here. Therefore, something like this, in fact, reduces to a different profile that looks more like something like this. So in other words, the plasma from the interstellar medium that is going through the shock is slowed down before it actually crosses the shock. Now, in shock acceleration, what really determines the spectrum is this jump in velocity, or this one. So one implication that follows from this very simple idea is that the simple power law e to minus 2 that I gave you before actually fails. So you don't have a power law anymore. Once you take into account the nonlinear reaction of the particles that are being accelerated on the accelerator. And typically this results in stuff like this. So in this plot, the standard result would look like a horizontal line. E to minus 2 would look like a horizontal line. And you see, in fact, that the spectra all look like concave. But the second implication that follows trivially from energy conservation is that if you're accelerating particles, it means that part of the energy of the system is being channeled into accelerating these particles. Therefore, there is less energy available for heating the plasma behind the shock. Therefore, the peak of the Maxwellian of the thermal distribution, when you accelerate more and more, moves towards lower temperature. Okay? So the two main consequences of taking into account the energy of the particles is that the particles are not accelerated anymore to a perfect power law, and the second is that the gas behind the shock gets cooler. Of course, this is not just an academic amenity, because the temperature behind the shock is something that you measure from X-ray observations. So you have to keep track of these physics. The second point, however, is probably more interesting. This is a picture of Tycho, supernova remnant. And this tiny filament here, all around the shock, it's almost spherical, is the result of non-thermal synchrotron emission from high-energy electrons. The fact that it's so thin reflects the fact that particles that are producing it lose completely their energy while they are radiating. That means that by measuring the thickness of this filament, you can actually infer how much magnetic field was there. And when you do this exercise, you get a magnetic field which is about 100 microgauss, up to a milligauss in some cases. Now, this is about 100 times larger than the magnetic field in our galaxy. So clearly, something very local is happening in this region to change dramatically the condition with respect to here, which is immediately before the shock, where the field is only a microgauss. So what we think is that the particle acceleration itself is creating the scattering centers and is amplified the field at the shock front so as to allow the particle energy, so as to allow the acceleration of the particles. And interestingly, when you include this effect, the maximum energy, of course, goes up quite a bit. Why is the field actually amplified? Well, I'm trying to do this in 2 slides, and it's not exactly a topic for 2 slides. But let's try to give an idea of what's going on. So let's imagine that this is the shock front. And there are cosmic rays that are being accelerated at this shock front. And let's say that they are all protons, so that there are a bunch of positively charged particles that are moving with the shock. Particles moving, it's a current, right? So you have a current that is flowing this way. Plasmas don't like currents, so they try to react in such a way to compensate for the charges that are present there and cancel the current. So what happens is that the plasma here in which the shock is moving moves slightly electrons and protons with respect to each other so as to compensate for the charge of the cosmic rays themselves. Now, this situation is unfortunately, or fortunately for us, unstable in the sense that when you have 2 streams that are counter-streaming, 2 flows that are counter-streaming, this gives rise to an instability. And if the energy density in the current is larger than the energy density in the pre-existing magnetic field, and this is always the case at the shock front, then this instability is turned on. It grows quite fast, but it grows at scales which are very, very small compared with the Larmor radius of the particles. So you can imagine that the amplitude of these waves grows a lot, but on scales which are very small compared with the Larmor radius of the particles. So according to what I told you before, particles don't react much to this perturbation, right? However, at the same time, while this current is moving, and there are all these tiny perturbations that are being excited, the plasma in the same region, this is the equation of motion for an element of the plasma, feels the force, which is the delta B on these small scales multiplied by the current. It's just a basic electrodynamic law. And you can calculate how much this plasma motion, this plasma element moves under the action of this force, and you can calculate that. And basically the instability stops growing when the size of these loops becomes of the same order of the Larmor radius of the particles. You can calculate when this happens, and interestingly, you didn't put this by hand, but what you find at the end is that it stops growing when the energy density in the perturbations is the same as the energy density in the particles that are producing it. So it's a sort of a equipartition. So the idea that is developing in present times is the following. You have a shock wave. Imagine that there is one generation of particles that are crossing the shock and maybe going back on the other side. At this time, they propagate in a medium in which they do not have anything to scatter on. But it's a current. As I told you, it's unstable. It produces perturbations. So the next particle that tries to do the same thing starts diffusing. The energy increases by a little bit, and the cycle repeats, because now the particles have larger energies. Again, they don't have perturbations to scatter on. They produce additional scattering, and so on. Now, hybrid particle in cell simulations have actually showed this in a much more precise form. So you see here the perturbations in the field that are present way upstream of the shock wave. And these wiggles here are the particles that are moving upstream and eventually returning by scattering on these perturbations. So the idea seems to qualitatively work, even keeping into account this strong interaction of the charged particles on the environment. The maximum energy that you can reach in a supernova remnant depends quite strongly on the type of remnant, but for supernova type 1, it's about 100 TeV. For a supernova type 2, in some cases, you reach about a PeV, but that's just to tell you how strong it is, how difficult it is to accelerate these particles up to very high energies. I'll skip this, but I will be glad to come back on these issues later. I wanted to switch to the part on transport of cosmic rays. How much time do we have? How much? Think again. Okay, that sounds already better. I want to switch to discuss a little bit of the transport of galactic cosmic rays from the sources to us. Now, the way that this is done it's done in a variety of ways. Some of them are very analytical, some of them are extremely numerical based. But the essence, the basic physics that is contained is really essentially the same. And you can understand the basic part of the transport with a simple elementary one-dimensional diffusion equation, then add a lot of complications on top of it, but the basic physics is really simple. So particles are injected in some place, say in supernovae maybe, or it doesn't matter, it doesn't need to be supernova remnants. Let's assume that they are injected only in a very thin disk, which is the disk of our galaxy, and then they diffuse under the action of turbulence, so the action of scattering of waves in the interstellar medium. So the idea is that you have sources in the disk and they diffuse in the halo. Okay? The equation, this kind of equation can be solved very easily. And what you get is that the equilibrium solution in the disk where we have the honor to live as a solar system is the injection term. These are just normalization factors. But the injection term, which is depending on momentum, like to P2 minus gamma, divided by the diffusion coefficient. So what we see at the Earth is steeper than what is injected by exactly this P to the delta, which is the energy dependence of the diffusion coefficient. This is the way that is usually done. Now, very essential to this business is the so-called assumption of free escape boundary. In other words, in all calculations, including the most complicated ones, you always assume that there is a boundary that we call the halo, at which the particles are free to escape away from our galaxy, ballistically. So these particles reach this place and they are free to go. The physical reason why it is so important, of course, that you assume stationarity. So if you inject these particles from whatever the sources are, you need them to escape somewhere, otherwise you don't reach stationarity. So that's the assumption that you do, that you make. Now, the free escape boundary reads that the function f at the edge of the halo must be 0. Now, of course, if you assume this, and you calculate the flux, which is d nabla f, the flux must be constant based on this equation, right? That means that the flux that reaches the surface, d equal h, the size of the halo, must be equal to some flux of particles that are escaping the system. And so that's just, I'm trying to say that this f equals 0 is, of course, some physical, but it's a good approximation. It just means that f out, outside the halo, is much smaller than the distribution function inside. Now, this simple picture, however, does not agree very well with what we see. There have been many surprises, observational surprises in the last few years. Most of them came from the alpha magnetic spectrometer experiment on board the International Space Station. So first of all, the spectra of nuclei have showed unexpected breaks, all of them at about 300 gigavolts rigidity about. The proton spectrum seems to be different from that of all the other nuclei. Helium, carbon, oxygen, they all share some commonalities, but protons seem to be a little bit different. Positron axis, the positron that we observe are wildly different from the ones that we were expecting. So just a few plots to show this. All these things that are falling down are what we were expecting based on simple idea I showed you before. And you see that all the components seem to have a hardening at high energy, which is usually named discrepant hardening. At the same time, let me go here first. At the same time, this is very important, the electron spectrum and the positron spectrum are extremely different from each other. And this is an interesting plot. These are all the primary spectra. These are all the secondary spectra, lithium, beryllium, and boron. Why is it that beryllium, boron, and all the secondary spectra should be steeper? Well, the reason is very simple. As we saw before, what we see as equilibrium spectrum of protons, let's say, or any other primary, is the injection multiplied by the diffusion time, which is 1 over the diffusion coefficient, right? Therefore, again, you have E2 minus gamma, which is the injection, the first term, times E2 minus delta, which comes from the diffusion time. Now, let's do this for a secondary, say for a boron nucleus, for instance. Well, again, the law is exactly the same, but the injection of secondaries now, the injection of secondaries, say boron, is proportional to the spectrum of the primaries, so whatever is producing these nuclei as a result of spallation reactions, times the cross-section, which is, however, is energy independent, right? So this is now proportional to E2 minus gamma minus delta, as we saw, right? But this is the injection spectrum. The equilibrium spectrum of boron must be, again, the injection, QB, multiplied by diffusion. That means that this is E2 minus gamma minus 2 delta. So the ratio between secondaries and primaries must drop in energy like E2 minus delta. That's the basic thing that we're trying to say. Oh, it doesn't matter. So it is qualitatively okay that all these secondaries are falling with energy. What is kind of outside the scheme is the fact that at high energy, this primary spectrum seems to be coming up. Now, there have been a lot of investigations of the origin of this spectral break. There is a beautiful work by Giannolini and collaborators in which they show that most likely this spectral break is associated not with sources but with the transport. And there have been a bunch of explanations, of different explanations of how this, what we can learn from this spectral break. What I want to concentrate upon is, again, the idea that I was talking about before, namely that cosmic rays are actually able to generate their own scattering. So the idea that I want to pursue is the following. You remember before I told you that if you have a beam of particles that is shooting in one direction, the fact that the particles are spreading because of diffusion automatically leads to the conclusion that you have production of additional scatterers. Now, at the same time, we know that the interstellar medium is continuously stirred by, for instance, supernova explosions and other sources of turbulence. And next time you drink your coffee and you put some milk in it, try to follow what happens when you stir the system on a size which is order of magnitude the size of the cup. But when you look at it, you will see that there is power on much smaller scales. And this is the typical cascading that happens in any fluid system. Now, the interstellar medium is a little bit more complicated than that because of magnetic field, which makes one direction different from the other. So turbulence develops in a different way along the field and perpendicular to the field. But qualitatively, the idea is the same. You inject power, you inject turbulence on large scales, and this power cascades towards smaller scales. And remember, I told you that this perturbation is important for cosmic rays only when it reaches the same scale as the Larmor radius of the particles. Now, if you take a supernova, this big 10 parsec, 20 parsec, 100 parsec, and the scale of the resonance is several orders of magnitude below that scale, you easily imagine how much, you have to, how much energy scales you have to cross in turbulence before you get there. On the other hand, on the left side, the mechanism of self-producing, of self-production of this turbulence automatically works on the right scale. So turbulence is produced on the same scale as the Larmor radius of the particles, okay? So the two are typically operating at the same time. So in principle, what you should be doing is really to solve for the diffusion coefficient, taking into account that that turbulence is injected on some very large scale and cascade down, but it's also produced by the particles themselves. So this results in diffusion coefficient that instead of being just this e to the delta, as I always write, it results in something a little bit more complicated. And when you make a convolution of this with whatever you inject the supernovae, you automatically get that the spectrum has always a flexion at about 300 gigavolts or so. The energy at which the transition is occurring is actually pretty solid in the sense that once you know the normalization of the first and the second component, it comes out for free. So it is interesting that maybe what we are seeing is really the transition between self-produced turbulence and turbulence that pops down, cascades down from very large scales. I have to speed up a little bit, right? Another example of the action of non-thermal particles on the environment is a phenomenon that happens on galactic scales. Now, the fact that particles escape from a halo automatically says that if the density of particles is very small up here because of a free escape, but particles are injected in the disk, there is a force, there is a gradient of the pressure of cosmic rays that points in this direction, right? At the same time, however, the dark matter in our galaxy or in any galaxy pushes the gas towards the center, right? So the gravitational potential exerts a force in this way. So you understand that if the gradient of cosmic rays, which is a force, is larger in some location than the force associated with gravity, the gas there is lifted off in the form of a galactic wind. Now, this in fact must happen at least in several locations in a normal galaxy like our own. And there are a bunch of simple implications of this. The actual thing is complicated, but the simple implication is the following. The fact that gas is lifted off, it means that particles are also advected away or convected away with this outflow from the galaxy. So in order to understand if diffusion is more important than convection, you need to compare these two scales. And you see that there is always a scale which is energy dependent, which is momentum dependent, where one stops being important and the second becomes important. This is as if, not exactly the same, but as if the particles are leaving the system, not at the edge of the halo, but rather at some distant z star, which becomes a function of momentum. Now, this very simple line of reasoning automatically leads to spectra in the galaxy, so inside where we are sitting, which are profoundly different, whether there is an outflow induced by cosmic rays or there isn't. So you see very easily how something on scales which are 10 or 100 kiloparsec directly affects what we see in the disk of our galaxy in the form of cosmic rays. So the microphysics of the force exerted by cosmic rays on the background plasma directly affects, as a back reaction, on what we see in terms of spectrum at the place where we are sitting. I want to spend just a few words, a few minutes, I guess. I have 5, yeah, on something that I have been thinking of in recent times. And this is, again, a sort of a toy model, or if you want, it's one of those demonstrations in which in mathematics you start from an assumption and you want to derive the opposite conclusion. So this is our toy model of the galaxy. There's a disk here, and cosmic rays are diffusing, and eventually they reach a place where there is free escape and they leave, right? More physically, maybe what is happening in nature is that you have a magnetic field that is dropping in energy. The diffusion coefficient always follows the opposite trend, so it grows. Remember, free escape means it's the limit in which the diffusion coefficient tends to infinity, okay? So what we can reasonably say is that what is happening is that the diffusion coefficient drops when you move away from the galactic disk. Therefore, diffusion coefficient comes up, and that's more or less what nature does to realize this free escape. Okay, let's assume that this is the case. Well, you remember I wrote this simple expression before. It just means that the distribution function at any place z above the disk is what we see at the Earth multiplied by 1 minus z over h. This is the solution of that simple toy model that I gave you before. Now, this implies that the flux of cosmic rays that I inject here at the disk is exactly the same flux that comes out of the galaxy. So this is saying something very trivial. Okay? Well, now we have the solution. So dn galaxy over dz is n galaxy that I observe at the Earth divided by the size of the halo. Now, a couple of comments. From Liouville theorem, since there are no losses here, what I inject must exactly be equal to what I escape, right? In fact, you see that while inside the galaxy, I observe eta minus gamma minus delta, so steeper than the injection. If I were sitting outside my galaxy, in fact, I would see exactly the same spectrum as injected. This also is telling me that independent of all the details, I know exactly how many cosmic rays are flowing away from my galaxy. I don't need to know what diffusion is and all these complications, because the flux that I injected must be exactly the same as the flux that escapes. So once I know the luminosity of my galaxy in cosmic rays, and I know the radius of the galaxy, then what I have outside my galaxy is well known. And I'm saying that it's free escaping. So again, this is a current that is propagating into the intergalactic medium. You remember that talking about supernovae, you have already seen this expression. So when the energy density in the particles is larger than the energy density in the magnetic field sitting there, in this case, the there is the intergalactic medium, I have this instability that is excited. Now, for these parameters, for our galaxy, this limit in magnetic field is of the order of 2 times 10 to minus 8 Gauss. So if the field outside my galaxy, our galaxy, is smaller than 10 to minus 8 Gauss, this flux of particles that is leaving my galaxy is going to affect the medium. In which way? Well, exactly the same way that I told you before for a shock wave in a supernova. It's going to produce these wiggles, and the growth rate of this instability is unbelievably short. It's of the order of a year. And again, imagine we're talking about scales that are now 10 to 100 kiloparsec. So this is nothing in terms of time scale. Okay? In 1 year, these wiggles are going to grow nonlinearly. So what we actually calculated here is that if the field outside our galaxy were smaller than 10 to minus 8 galaxy, 10 to minus 8 Gauss, automatically cosmic rays would produce exactly that field. So around any galaxy, including our own, you must have a field of the order of 10 to minus 8 Gauss, just as a direct implication of the fact that cosmic rays are escaping us, are escaping from the galaxy. And this is a large-scale field, so we're talking about several tenths of kiloparsec of distance from our own galaxy. Not only that, but so now you imagine, I got exactly the opposite conclusion. I told you before that cosmic rays were streaming, and now I'm telling you that they produce a field on a scale of their alarm radius, therefore they start diffusing. So I got the opposite conclusion. So what happens? Well, when they start diffusing, they develop huge gradients, because you imagine that now the density is increasing dramatically. By how much? It's increasing by a ratio which is roughly the speed of light divided by the Alfvén speed. Alfvén speed is about 10 kilometers per second, so it's increasing by 5 orders of magnitude. But as we learned from basic courses, a gradient in pressure is a force. So once particles are trying to escape our galaxy and they produce this field, at the same time, they couple very strongly with the background plasma and they push it. So they exert a force on the intergalactic medium which pushes it away at a speed which is roughly the Alfvén speed in the omega baryon rho critical that we have outside our galaxy. So omega baryon rho critical multiplied by some overdensity delta, which is probably of the order of 100 or so, because the galaxy is a virialized structure. So within the virial radius, it's the definition of the virial radius that the density inside is on average 100 times larger than omega baryon rho critical. So as an implication of the assumption of free escape, I got as a consequence that cosmic rays must be producing field there and pushing the gas away roughly at 10 to 100 kilometers per second velocity. I also told you that the fact that they cannot escape freely, but they are slowed down by diffusion, also increases their density. Again, this is almost trivial, but it's an important fact. Therefore, the interaction of these particles with the background intergalactic medium there must produce secondaries, for instance, gamma rays and neutrinos. And this is the flux of neutrinos from ice cube, and these green lines are what I get from calculations, assuming that the overdensity is of order 20 or 100 or 200. And it doesn't look very different from those. So at least some of these neutrinos that we think they are associated with extragalactic distant sources might in fact be a sort of a byproduct of the fact that cosmic rays are trying to stream away from our galaxy. But at the same time, they self-break by as a consequence of their interaction with the intergalactic medium. Well, I don't have time to go beyond the standard model, so I'll switch this part. But there are a bunch of people that are starting to put out ideas that a few years ago would have been completely heretical, and now it's probably a little bit less heretical. I'll answer questions about that if you want. But I just want to draw some very general conclusions. One is that why should we study cosmic rays? Well, because cosmic rays involve interaction of charged particles with the background environment. Whether that environment is a supernova remnant or the universe or the galaxy, it doesn't really matter. And this process of transport of charged particles in the medium is at the very base of all non-thermal phenomena in the universe. Whether you want to apply these concepts to gamma ray bursts or to neutron star mergers or to a supernova or to other things, it doesn't really matter. But cosmic rays are important because it gives us access. They give us access to this common ground, if you wish. In a modern language, this is translating into an increasing need to see cosmic rays as a part of a bigger thing, of a bigger system. So that cosmic rays are not just passive spectators of whatever happens, but they actually modify, for instance, galaxy evolution through the injection of cosmic ray-driven winds, for instance, or they affect clusters of galaxies through the interaction of the cosmic rays with the intercluster medium and the production of magnetic fields there. It also has, we can benefit from huge success in radio, X, gamma, and neutrino, and more recently gravitational wave astrophysics, because all of them give us inputs from other environments on how particles are energized in systems which are very different from the ones I mentioned here. And maybe for particle physicist aficionados, maybe we can think of or dream of the opposite way. You know, we accelerated particles at LHC by electric fields and magnetic fields curving their trajectory. But clearly we got to the limit of it, right? I mean, it's very hard to imagine building something bigger than LHC. But clearly nature has figured out how to accelerate particles to energies which are way in excess of the ones we have. Of course, the accelerator is pretty big, but people are starting to think about plasma accelerators, for instance. Of course, this is very primordial right now, but people are starting to work on accelerating particles with soliton beams and stuff like that. And the first, tiny results are being seen. I'm not saying that this is already ready to replace any of the accelerations that we do and that we are experienced during the last century or so. I'm just saying that maybe we can learn from how nature works and maybe accelerate in the future particles on Earth with mechanisms which are a little bit different. Okay, thank you. I'll stop here.
So thank you, Pasquale, for this brilliant talk. Questions?
Thanks. Thanks for the great talk. I'm interested, amongst other things, in the formation of the magnetic fields in astrophysical shocks. And you showed that the presence of cosmic rays leads to a sort of equipartition between the magnetic field energy and the cosmic ray energy. So I have two questions regarding that. The first is, in this new vision, how does the magnetic field energy scale to the actual kinetical energy of the shock? And secondly, what are the implications in the geometry of the magnetic field? Is it contained in the shock, or is it perpendicular? Because that has implications, for example, for polarization measurements of shocks and other phenomena.
Yeah, very good question. So it scales roughly like a rho v cube. So it scales like the cube of the velocity of the shock, roughly. This is the strength of the magnetic field. The second question about the polarization or the structure of the field. So the field in the ISM is typically a few microgauss, right? The field that is generated here is about 100 times larger. So in the end, it becomes almost isotropic behind. I mean, the original field becomes almost irrelevant, right? But, so imagine that this is a shock surface, and the field is amplified upstream of the shock, so before the plasma crosses the shock wave. So even if you accelerate the three components in the same way, in the sense that the field is isotropic, while crossing the shock, two of the components get amplified by a factor of 4, because of the shock compression. So behind the shock, you are likely to have a field which is imbalanced in the direction perpendicular to the shock normal, so parallel to the shock front. However, the turnaround time of these scales is very quick. So when the plasma is at vector behind the shock, you expect typically this to cancel out. So the polarization, if any, the polarization would remain affected by this compression only within a tiny layer behind the shock. I'm not sure that it is actually observable once you compare it with the angular resolution of the polarimeters we have, or the ones that we are thinking of. But there are people working on this. One of them is Andrei Bykov, who's trying to study the effects of this mechanism on the polarization of X-rays. It's important to do it with X-rays. With radio waves, it wouldn't work because electrons generated in the radio waves have a very long lifetime. So the radio signal would average over a long time behind the shock, right? X-rays, because of what I said here, are actually probing a very small region behind the shock. So X-rays are all produced in these very small filaments, right? So those are typically about a 1/100th of a parsec in size. So they're very thin. And so if we could actually measure the polarization signal in these tiny, narrow filaments, it would be a useful piece of information. I'm not sure that with the angular resolution that is available, we can do that, but it's definitely an interesting thing to think about.
Regarding this problem of polarization, do we are able to measure it or not? Polarization was observed in gamma ray bursts. Therefore, I don't know, there is any difference between, for instance, these shocks which are not relativistic and gamma ray bursts which is relativistic?
Yeah, there is a 4 gamma squared times in the relativistic case. So,
and
yes,
does it affect the polarization, the amount of polarization?
Well, it just means that the perpendicular components of the field are amplified by gamma squared times, right? Yes. And if gamma is of order 100 or so, this is a huge factor. Here, it's only a factor of 4. And that's what, I think that's what the main difference.
Other questions?
I think there are already laser experiments where people try to accelerate particles by creating shocks with laser, but not the most extreme energy that you mentioned. But I think there are already people trying to do such things with lasers.
There are 2 examples. One is use lasers, the electric field of the laser to do it. So not creating a shock, but rather creating a sort of a soliton. So the particle is actually surfing the electric field of the laser. The other idea is to shoot a laser on a target and produce a collisionless shock out of the interaction of the laser with the target. And then the shock does whatever it has to do. I think we are a long way from accelerating particles at such a shock. But yes, there have been people working on the acceleration at the electric field of the laser. Yes.
Okay. Unless there are any other urgent questions, maybe we stop here and we can thank Pasquale again.